All right, back in 2015, this one paper comes out and it doesn't just, nudge AI forward a little bit. No, it completely shatters a wall that was holding the entire field back. See, there was this really weird paradox happening. People were trying to make neural networks deeper, thinking that would make them smarter, but it was actually making them worse. This paper solved that, and in doing so, it basically kicked off the age of ultra-deep AI that we're all living in right now. So let's get into this super simple but totally brilliant idea that made it all happen.
Okay, so here's how we're going to break it down. First, we'll look at this totally counterintuitive problem that had everyone scratching their heads. Then, we'll get into the elegant solution they came up with. After that, we'll see how it absolutely smashed all the existing benchmarks. And finally, we'll talk about the huge legacy this thing has today. All right, so let's set the scene here. We're talking mid-2010s. The common wisdom in AI, the thing everyone believed, was pretty simple. Deeper is better. Right? More layers in your neural network means it can learn more complex stuff, so it should be way more powerful. But there was a huge problem. In the real world, the exact opposite was happening. And this chart right here, it shows you the problem perfectly. This is data straight from the paper, and it shows something that honestly just shouldn't be possible. The taller bar, that's a 56-layer network, and it has a higher error rate than the shorter 20-layer one. And get this is on the training data. So it's not even about struggling with new information. The deeper network was failing to learn the very stuff it was supposed to master. It just makes no sense.
So this was the big question, right? Why? Why was adding more layers making these things dumber? And it wasn't the usual suspect, overfitting. Logically, a deeper network should, at the very least, be as good as a shallower one. I mean, think about it. It could just copy the layers from the shallow network, and then the extra layers could just learn to do nothing. Just pass the signal straight through. But they couldn't. For some reason, these networks were getting totally lost in their own depth. The whole field was basically stuck.
So how do you fix a problem like that? Well, the authors of this paper came up with this brilliant shift in thinking. They thought, okay, instead of making the network learn this incredibly complicated thing from scratch, what if we just ask it to learn the difference, just the little bit that's needed to get from the input to the right answer?
Yeah, think about it like this. What we were doing before was like giving an artist a completely blank canvas and saying, go ahead, paint the Mona Lisa. That's a huge, overwhelming task, right? The network had to figure out every line, every shadow, every single little detail, starting from absolute zero. But with this new idea, residual learning, the whole game changes. Now, instead of that blank canvas, imagine you give the artist a pretty decent sketch of the Mona Lisa, and you just say, okay, your job isn't to paint the whole thing. Your job is just to learn the residual. The final touch-ups, the corrections, the details that turn the sketch into a masterpiece. All of a sudden, the job is way, way easier. The network isn't learning the whole picture anymore. It's just learning the change, the delta. And this is how they did it, with something they called a shortcut connection. It's genius. So the input, let's call it X, goes into a few layers like normal. Those layers are trying to learn that little change we talked about, the residual. But at the same time, the original X gets to take a shortcut. It completely bypasses those layers and meets up with their output on the other side. And what happens then? They're just added together. That's it. That simple act of addition is the whole trick. And this is what solves that whole degradation mystery. Because now, if adding more layers isn't actually helping, the network has a super easy way out, an off-ramp. All it has to do is learn to make that residual part 0. If it does that, then the output is just 0 plus the original input that took the shortcut. In other words, the layer has learned to do nothing, to just pass the information through untouched. That's the one thing these deep networks were failing at before, and this simple trick made it trivially easy for them. So with this new architecture, which they called ResNet, short for residual network, the researchers didn't just solve their little problem. Oh no. They completely blew the doors off the existing state-of-the-art and showed everyone what was really possible. I mean, all of a sudden, they could train networks that were ridiculously deep, depths nobody thought were possible. They actually got a 152-layer network to work beautifully. And just to put that into perspective for you, the best models at the time, like VGG, were struggling to get past 19 layers. This wasn't just a step up, it was a giant leap. We're talking almost 8 times deeper. And the results, well, they speak for themselves. They took this thing to the ImageNet challenge, which is basically the World Cup of image recognition, and their model got an error rate of just 3.57%. That is insanely good. They practically cut the error rate of the previous year's winner in half, a huge, huge improvement. And as the authors themselves put it, this wasn't just some interesting academic finding. This was them winning first place. They took the gold medal in the Olympics of computer vision. It was a decisive win that basically established ResNet as the new king of the hill for, well, the entire field.
Okay, so the impact of this paper, it's hard to overstate. The shockwaves are absolutely still being felt today. See, the residual connection, that little shortcut, it didn't just give us a new model. It gave us a whole new way of thinking about building networks, a philosophy that really enabled the whole deep learning revolution that followed. Just look at this timeline. It says it all. You add AlexNet with 8 layers. Then a couple years later, VGG and GoogleNet get us to around 20. We're slowly, painfully, inching our way up. And then bam, 2015, ResNet comes along with 152 layers. It's not an inch, it's a pole vault. It kicked the door to ultra-deep learning wide open. And suddenly, networks with 1,000 layers weren't sci-fi anymore. They were something you could actually build. And today, the influence of that simple shortcut is literally everywhere. Of course, it's the foundation of pretty much all modern computer vision. Image recognition, object detection, you name it. But its legacy goes so much further. That exact same idea of a residual connection, it's a key part of the transformer architecture. The thing that powers models like GPT. It helps solve that classic vanishing gradient problem by giving the learning signal a direct highway to travel down, which is what allows these gigantic models to actually train without getting lost.
So when you boil it all down, what's the big takeaway here? I think if you look past all the math in the code, the core idea behind ResNet is actually surprisingly profound. Think about it. If the key to unlocking this incredible machine intelligence was to make it incredibly easy for the machine to do nothing, what does that say about how we learn? Maybe radical progress isn't always about building brand new, complex things from scratch. Maybe sometimes the real path to getting smarter is just about learning to make small, intelligent corrections to what we already have. It's about learning the residual.
This is for entertainment purposes only.